Condition for invertibility. Welcome, everyone. Before we dive into today's topic, let's take a quick look back at what we have already covered. In our previous lessons, we worked through the mechanics of matrix algebra, specifically learning how to calculate the adjoint of a matrix and how to apply the general formula to find an inverse. However, there is a crucial detail we haven't addressed yet. It is a common misconception to assume that every square matrix we encounter can be inverted. In reality, not every square matrix has an inverse. That brings us to our focus for today. In this subsection, we are going to move beyond just the how-to and look at the why. We will analyze the specific mathematical condition that determines whether a matrix is invertible, meaning an inverse exists, or non-invertible. By the end of this session, you'll be able to identify this status at a glance without having to perform all the heavy calculations first. Understanding invertibility. Now that we know we have the tools to find an inverse, we need to define exactly what it means for a matrix to be invertible. Think of a square matrix A. We say that matrix A is invertible if we can find another square matrix. Let's call it B, that acts as its perfect partner. Specifically, this partner must satisfy a very particular condition. When you multiply A and B together, the result is a times B equals B times A, which both equal the identity matrix. And remember, this identity matrix must be of the same order as our original matrix. When this special relationship exists, we refer to matrix B as the inverse of A, and in our notation, we write this as an inverse. However, it is important to note that this isn't always possible. If we search for such a matrix B and find that no such matrix exists, we don't just say it's not invertible. We use a specific mathematical term. We call matrix a singular matrix or a non-invertible matrix. As we will see in the next slide, there is a very specific mathematical test we can use to tell if we are dealing with a singular or an invertible matrix. Theorem 4. The condition for invertibility. Now that we have established the definition of what an inverse actually is, let's move on to the most important part of this lesson, the rule that tells us if an inverse even exists. On this slide, we encounter the fundamental theorem governing the existence of an inverse. This theorem is the golden rule for everything we are about to do. The theorem states that a square matrix, let's call it A, is invertible if and only if A is a non-singular matrix. Now, if and only if is a very important phrase in mathematics. It means this condition works in both directions. To make this even clearer, let's look at it in simpler mathematical terms. A matrix A has an inverse, which we denote as an inverse, if and only if its determinant is not equal to 0. In notation, we write this as the determinant of A, which is the absolute value of A, is not equal to 0. So, if you calculate that determinant and find it is anything other than 0, you are in the clear. But if it is exactly 0, you can stop right there, because an inverse simply does not exist. In the next slide, I will show you the algebraic reason why this specific condition is so critical. Breaking down the logic. Now, you might be wondering, why does the determinant being 0 actually stop us from finding an inverse? To understand the logic behind the theorem we just discussed, let's take a closer look at the actual formula for the inverse of a matrix. As you can see on the screen, the inverse of matrix A, which we write as an inverse, is equal to 1 over the determinant of A, multiplied by the adjoint of A. If we focus specifically on the role of the determinant here, notice that the term 1 over the determinant of A represents the reciprocal of the determinant. This brings us to a fundamental division problem that we've encountered since primary school. In mathematics, division by 0 is undefined. So, if the determinant of A is equal to 0, then the term 1 over 0 becomes mathematically undefined. Therefore, we reach a clear conclusion. Since we cannot perform this division by 0, the formula for an inverse simply cannot be computed whenever the determinant is 0. This is exactly why, as we will see in our next slide with a helpful analogy, a matrix with a determinant of 0 is impossible to undo or reverse. Real-world analogy, the information loss concept. Now, I know that looking at formulas and determinants can feel a bit abstract, so let's step away from the algebra for a moment and try to visualize what is actually happening. To truly understand this concept, I want you to think of a matrix not just as a box of numbers, but as a transformation, a rule that moves, stretches, or rotates points in space. First, let's look at a non-singular matrix, which is a matrix where the determinant, or the absolute value of A, is not equal to 0. Imagine you have a flat rubber sheet with a pattern drawn on it. When we apply a non-singular matrix, you might stretch the sheet or rotate it. However, because the determinant is not 0, the sheet remains a two-dimensional sheet. It hasn't been crushed or destroyed. Because the shape is still intact, you can perform the exact opposite movement to bring the sheet back to its original, pristine shape. This, reverse movement, is exactly what we mean when we talk about the inverse. On the other hand, let's consider a singular matrix, where the determinant, or the absolute value of A, is equal to 0. For this, imagine you are holding a 3D soda can. Now, imagine applying a transformation that crushes that 3D can down into a flat 2D circle. Once that can is flattened, the information about its original height has been completely lost. If I handed you that flat circle, you wouldn't know if the original can was tall and thin or short and wide. Because that original dimension has vanished, there is no unique way to unflatten it back to its original state. This process is irreversible, which is why, mathematically, we say the inverse does not exist. With this visual in mind, let's move on to some concrete, step-by-step examples to see how we apply this logic to actual numbers. Step-by-step example. Now that we have understood the theory and the logic behind why the determinant is so crucial, let's put this into practice with a concrete example. We are going to determine whether the following matrices are invertible by following the steps we just discussed. First, let's look at example A. We have a matrix, let's call it matrix A, which consists of a 2x2 arrangement. The first row contains the numbers 2 and 3, and the second row contains 1 and 4. To find out if this matrix has an inverse, we must follow step 1, which is to calculate the determinant of A, denoted as the vertical bars surrounding A. To do this, we multiply the elements of the main diagonal and subtract the product of the other diagonal. So, we take 2 times 4, which gives us 8, and then we subtract the product of 3 and 1, which is 3. This leaves us with 8 minus 3, resulting in a determinant of 5. Now, moving to step 2, we need to check our condition. We look at our result and ask, is the determinant equal to 0? In this case, our determinant is 5, and since 5 is not equal to 0, we can conclude that the matrix is non-singular. Therefore, our final conclusion for example A is that the matrix is invertible. This means we could actually go on to find its inverse if we wanted to, because the mathematical path is clear and we aren't facing any division by 0. Now, let's see what happens when the determinant actually hits 0 in our next example. Step-by-step example continued. Now, let's look at a contrasting case with example B. First, let's consider matrix B, which is a 2x2 matrix with 6 and 3 in the first row and 4 and 2 in the second row. To determine if this matrix has an inverse, we follow the same procedure we used in the previous example. Step 1 is to calculate the determinant of B, which we write as the vertical bars surrounding B. To find this, we multiply the elements of the main diagonal, which is 6 times 2, giving us 12. Then, we subtract the product of the other diagonal, which is 3 times 4, also giving us 12. When we subtract 12 from 12, we are left with a determinant of 0. Now, for step 2, we must check our condition. Since the determinant of B is exactly 0, this matrix meets the definition of a singular matrix. Therefore, our final conclusion is that matrix B is non-invertible. This means, unlike the first example we just saw, there is no mathematical way to find an inverse for this specific matrix, because the process would require us to divide by 0. In our next slide, I'll highlight some common pitfalls to avoid when performing these types of calculations. Common mistakes. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the theory, it is very easy to make certain mistakes during exams, so please pay close attention to these 3 points. First, a very common error is assuming that all square matrices are invertible. Just because a matrix has the same number of rows and columns doesn't automatically mean an inverse exists. You cannot take it for granted. You must always check the determinant first to confirm. Second, please be careful not to confuse the terms singular with non-singular. It sounds similar, but the implications are opposite. Remember, if a matrix is singular, it means the determinant of it equals 0, which means there is no inverse. On the other hand, if a matrix is non-singular, it means the determinant of A is not equal to 0, which means an inverse does exist. Keep this distinction clear in your mind. Finally, a major tip for saving time: do not start by calculating the adjoint of the matrix first. I have seen many students spend several minutes calculating the adjoint, only to realize at the very end that the determinant is 0. If the determinant is 0, the adjoint is actually irrelevant because the inverse simply cannot be computed. To work efficiently, always calculate the determinant first. If it's 0, you can stop right there. In our next slide, we will summarize everything we have learned today into a few key takeaways. Key takeaways. First, remember that an invertible matrix is simply a matrix that has an inverse, meaning there is another matrix that can undo its transformation. Next, let's clarify the terminology regarding the determinant. We call a matrix non-singular if its determinant, which we write as the determinant of A, is not equal to 0. On the flip side, we call a matrix singular if its determinant, or the determinant of A, is exactly equal to 0. If you remember nothing else from today, remember this golden rule. A matrix A is invertible if and only if the determinant of A is not equal to 0. This is the fundamental test you must always perform. Finally, why does this rule exist? The mathematical reason lies in the formula we looked at earlier. The inverse of A equals 1 divided by the determinant of A, all multiplied by the adjoint of A as we discussed, because this formula requires us to divide by the determinant, and because division by 0 is mathematically impossible, the inverse simply cannot exist when the determinant is 0. All right, we have reached the end of our lesson, so let's bring everything together with a quick summary of the key takeaways. Keep these points in mind, and you'll be able to navigate any problem involving matrix invertibility. Great job today!